Hello and welcome to this video for Chemistry 30 in the organic unit. This is Miss Simpson. In this video, we're going to finish the organic unit. We're going to look at different types of polymerization reactions and a couple of different refining reactions, cracking and reforming. Okay, so this will be, like I said, the end of the unit where we finish up looking at all our reactions, starting with polymerization. So there's a few different types of polymerization. Actually, if I go back here for a sec, you'll see there's addition and condensation polymerization. Condensation kind of has two subcategories depending on if you're forming an ester or an amide, which we've never really talked about until today. And then the two refining processes are cracking and reforming. Okay, so starting with polymerization. A polymer is when you have a base unit repeating over and over and over. Okay, the base unit is called a monomer. So when a monomer repeats bazillions of times, you produce a really large molecule called a polymer. Polymers can be natural. Some examples of natural polymers are carbohydrates, proteins, and the most obvious, DNA. They can also be synthetic. A lot of our plastics, nylon, Teflon, polyester, PVC are synthetic, so man-made polymers. Like I said, plastics is a really big use of polymers. Plastics are very important for us in our society, right? We have lots of uses for them. Unfortunately, they're becoming kind of a environmental problem with microplastics and everything and how long they last. Now, when it comes to naming a polymer, all you need to do is put the word poly in front of the monomer name, okay? So if I have my monomer as ethene, it'll become polyethene. They also have some classical names, and we'll look at those as well. So this is my example of forming polyethene, okay? You are always going to have two monomers that you add together, okay? They can be the same, they can be different. In addition polymers, they're usually the same, all right? So you might just see the reaction written as NC2H4, okay? N meaning multiples of these. You're going to just show how two of them bond, because remember, there's an infinite number of them bonding. You're just going to show how two of them bond to each other, okay? All you have to do for addition polymerization is very similar to an addition reaction. You are going to break the double bond apart and put the carbons together, okay? So there's 4 carbons that'll come together. This is carbon molecule 1, had 2 hydrogens on it. There was a double bond. That double bond is now broken, and it can continue to bond outward, which is where the second ethene molecule comes from. It had a double bond, but we broke the double bond so that it can also now continue to bond outward, okay? We usually put square brackets around this 2 molecules repeating with an N after it and ... showing that this continues to go on millions of times, okay? Now, again, the name of this polymer is not based on the polymer, it's based on the monomer, okay? So the name is polyethene. Even though it might look like butane right now, that's not what we call it. We put poly in front of the monomer name. Okay, so polyethene. And that's basically it for addition reactions. We'll do some more examples, and I'll even show you again some of the common names that they have, or classical names that you have. So this again was polyethene. Here is, again, an infinite number, but we're going to show 2 of them reacting. So I have 2 carbons, and they each have fluorines, 2 fluorines on them, okay? I'm going to react 2 of these. So I'm going to be having 4 carbons put together. Now I need to name this monomer. It is called tetrafluoro ethene. Okay, and so when I put them together, again, there will be 4 carbons that end up together with single bonds between them because the double bonds have broken. And they each carbon had 2 fluorines on it. So, right, this is molecule 1 where the double bond was broken. And then this was molecule 2 where the double bond was broken so that they can continue to bond outwards. I put an N and a dot, dot, dot. So the name of this, the IUPAC name, would be polytetrafluoroethene. Okay, again, you just put poly in front of the monomer name. That's the IUPAC name. Okay, but if we were to look at the classical name, that's Teflon. Okay. Next, let's say we have chloroethene. So here's my ethene. It only has 1 chlorine on it. Okay, so that's chloroethene. I'm again reacting 2 of them to show how at least 2 of them join. Again, remembering multiples of these are joining. Again, we have catalysts involved for this reaction. So I have my 2 carbons with 1 chlorine on one of them. The rest are hydrogens. And then it's bonded to another 2 carbons with 1 chlorine on one of them. And then that is your polymer. The name, the IUPAC name, would be polychloroethene. Okay? And if I erase this and put up the classical name, this is PVC, polyvinyl chloride. Okay? And then the last example here, we have phenylethene. So I have a phenyl branch, that's a benzene ring, on one location only, because it's not di or tetra or tri phenyl, it's just one phenyl. Okay, so putting them together with a catalyst, again, I have 2 carbons. One of the carbons has a benzene ring, the others don't. There's my other 2 carbons. One of them with a benzene ring, and the other ones are hydrogens, and so on. Okay, so this is IUPAC polyphenylethene. Okay, polyphenylethene. And again, the classical name of this one is, I believe, styrofoam. Polystyrene, also known as styrofoam. Okay, you don't have to draw the H's like before. You can just draw lines going to nothing, or you can draw the H's. So if you were given the product and you wanted to figure out the reactants, you would just split it in half and put a double bond between those carbons. Okay, they also don't only have to be ethenes. These were all ethenes. They could also be a propene. You're going to break the double bond and join the carbons together where the double bonds broke. Okay. So that is addition polymerization. Next, we'll look at condensation polymerization. These ones are a little bit more complicated. You're going to have usually different monomers reacting, and water is going to be a product as well as your polymer. Okay? So the monomers are going to have 2 functional groups, one on each end, so that they can continue to join. And the 2 ways this can happen is either called ester linkage, very similar to making an ester, or amide linkage. Amide linkage is when you have nitrogen as part of your molecule. Okay, so I will show you an example of these and it'll make more sense. Basically, you're treating it like a puzzle. You're removing water and putting the molecules together. Okay, so we'll start with our ester linkage. You will not be expected to name a molecule like this that has 2 acid functional groups, 2 carboxyl functional groups. But you could name this one. This is ethane dash 1, comma 2 diol. Remember, we keep the E if it ends in diol. So this is ethane 1,2 diol. Okay? That's the only one you could name. You can't name this one because it has 2 carboxyl functional groups. Now, what's going to happen in this reaction? So in molecule 1, this is molecule 2. Notice how there is a carboxyl functional group on each end of that one and a hydroxyl functional group on the end of these ones. So there's 2 functional groups on each of them. Okay? That's important because if there was only one functional group, this would be removed as a water molecule and I would just form an ester. It wouldn't be condensation polymerization. Okay? It would just be esterification. But because there's another end, this is also going to lose its OH and its H, so that these can continue to bond outward, continuing the polymerization. Okay, so my pen's being silly right now. What we're going to do, like I said, is I'm going to remove this H, remove this H, remove that OH, and remove that OH. Some textbooks actually also, just a heads up, some textbooks remove the OH from the acid and just the H from the alcohol. So you might see it done either way. Still, you're removing waters, okay? I usually, like we did with esterification, like to remove just the H from the acid and the OH from the alcohols. So what you're going to produce is N waters. Now, some students say, but there's 2 waters. There are 2 waters, but this is happening multiple times. So it's a huge number of waters. So we just put N water, okay? And then my polymer is going to be what's left over joined together, okay? So I'm just recopying these molecules down here. So what's left of my acid is an O that's going to bond outward, bonded to a C, double bonded to O, bonded to the benzene ring. Okay, I'm just copying this diagram and this diagram together down here. Okay, so this was also bonded to a C, double bond O, bonded to an O. So that's it for this molecule drawn down here with the H's removed. Now I take this molecule, bring it down here. The OH was gone, so all that's left are 2 C's, and it'll continue to bond outward. Okay, don't forget your H's though. And that is your polymer. I would not expect you to name this either. Okay. The only one you could name is the ethane 1,2 diol. This is PET, and this is our what we call ester linkage. Okay, it's like we're forming an ester, but it's going to continue on both sides and continue to repeat over and over. And N waters, that's why it's called condensation polymerization. Condensation, think of water. You're producing water as well as your polymer. Okay, so that is the ester linkage. Then we're going to look at the amide linkage. Okay, so this is the amide functional group. N with 2 H's. Remember, your nitrogen, back to Chem 20, can form 3 bonds. Okay, so if it's bonded to a carbon, it's going to have 2 H's on it. All right, and now what you're going to do here is on your acid side, you're going to remove, so these are 2 of the same monomers, but they again have 2 functional groups. You're going to remove the OH on the acid and 1 of the H's on the nitrogen. Okay, so again, we're going to form multiple waters, 2 for each 2 monomers, right? And then we put them together again like before, what's left over. So this is my carbon left bonded outwards to continue joining with the rest of this polymer. It's double bonded to an oxygen, bonded to a carbon that has 2 hydrogens, and bonded to a nitrogen that has only 1 hydrogen left, and now it continues to bond to the next molecule. So a carbon double bonded to oxygen, bonded to a carbon with 2 H's, bonded to an N with 1 H left, and it continues again to bond outwards. Okay? So that is known as your amide linkage, where you have carbons and nitrogens bonding together. Oh, sorry, I believe it's actually the carbon double bond O. That's your amide linkage. Okay, this is what a protein looks like. I'm going to erase this and put it up just to make sure we did that all correctly. Okay, so the amide linkage, yes, is the N to the C double bond O there, right? Okay, so here's a sample diploma question. You are given the following polymer. Now, it's partly condensed, partly complete, so I'm gonna draw it all out just so it's easier for me to see. I have C with 2 H's bonded outward, bonded to a C with 2 F's, bonded to another C with 2 H's, bonded to a C with 2 F's, bonded outward, okay? So this should make sense to you. There's no water, so it's an addition polymerization reaction. And if we split it in half and then put a double bond, I'm getting my monomers. CH2, because these are now gone, CH2, CF2. So the answer is C. Oh, my answer's not coming up there. Answer is C. Okay? The last thing we have to look at is different refining processes that we have, and especially living in Fort McMurray where we live, this is something that you should maybe already be familiar with. So a lot of petroleum is refined and then burned as fuel. Some is also used in the production of plastics. There are a few different processes that are involved in refining. One of them can be something called fractional distillation. Okay? Distillation is when you separate molecules based on their different boiling points. But this is called fractional distillation because we're going to have multiple different compounds, multiple different boiling points in a big, what we call fractional distillation tower. Okay? In the tower, the lighter molecules are going to have a lower boiling point and therefore be at the top of the tower, whereas the heavier molecules with a higher boiling point are going to be lower in the tower. Okay, so for example, this is what that tower looks like. I have my gas with probably methane at the top. Methane has 1 carbon, whereas at the bottom I have bitumen, which is a big mix of compounds, but it's going to have lots of carbons and lots of hydrogens, okay? So small molecules with less carbons are at the top, large molecules with more carbons are at the bottom, okay? So that's a fractional distillation column. Again, they're being distilled at different levels based on their different boiling points. You can also have something called solvent extraction. Okay? Solvent extraction is when you are separating them based on their solubilities. So you're starting with this solution. You have some solute, the black particles dissolved in the solvent. You're going to add another solvent that is not soluble with the first solvent, so it forms 2 layers. And then these solute particles actually move into the other layer because they're more soluble with that layer. Okay, so the solute particles are going to move to the top layer. Then you have the original solvent left on its own, and you can just drain it out to remove it. Okay, so that's what solvent extraction is known as, where I'm getting rid of this blue or green solvent because it has a different solubility than the other solvents that we're switching the solute particles into, right? Now, there are also two types of reactions in refining, and they're actually just opposite of each other, cracking and reforming. So cracking is where you add hydrogen and you break a long chain into two smaller chains. That's it, okay? Usually involving alkanes in these processes. So here's an example. Now this is a shortened way of showing a hydrocarbon. These are all the middle carbons that have two hydrogens, and then your two end carbons have three hydrogens on them. So it's kind of a condensed method of showing a formula. So in total, I have C15, 16, 17, C17, H's 30 plus another 6 is 36. Okay? You are not expected to name organic molecules that have more than 10 carbons. So you wouldn't need to name this, but I'm reacting it with hydrogen gas. Okay? And I'm going to make two smaller units. You're going to be given one of the units. So this is C6 plus two more C's. So C8, H18, you could name this. This is octane. And then your other product has to be the remainder of the original molecule. So the molecule had 17 carbons. 8 of them made molecule 1. So that means we have another 9. I believe, if I'm doing my math right. I'm trying to do my math in my head, and that always is a mistake. So 17 minus 8 is, yes, 9. And our H's would be double plus 2. So double would be 18 plus 2 would be 20. And so this would be nonane. Okay? If you wanted to write this formula like this, it would be H3C, and it's written as H3C instead of CH3 to show that it's the carbon bonding to these middle carbons, not the hydrogen. That's the only reason it's written like that. If I have 9 and two end ones, right, because the two end ones are shown there, that means I have 7 in the middle. Okay? Or you can just be given the chain as one whole thing, add it up. I have 1, 2, 3, 4, 5, 6, 7. C7, that would need double plus 2 would be 16. This is heptane. This is one of your products. I just ran out of room, so the products are being written below here. I'm adding again H2. And I'm forming C4H10 as one of my products. That would be butane. So my other product would need to be C3H8 to add up to 7 carbons to match the 7 from your original hydrocarbon. So that is propane. And then I could, let's draw a line diagram for that. 1, 2, 3 carbons. That makes it a lot easier if you just draw a line diagram. Okay? So that is cracking. You're adding hydrogen to break your large hydrocarbon into two smaller hydrocarbons, okay? Reforming is the opposite. You are taking two small hydrocarbons, removing hydrogen, and putting them back together to make one large molecule, okay? So for example, C7H16 would be heptane. I can't name that one because it's more than 10 carbons. Hydrogen is one of my products, and the other product is putting the C's together. So 12 plus 7 makes 19 carbons, and then your hydrogens would be double plus 2 would be 40. Now this all balances, by the way. If I add these hydrogens together, 16 plus 26 gives me 42 hydrogens on this side. I have 40 here plus the other 2 here, which adds up to 42. Okay, so your carbons and hydrogens all balance. These don't all go together to make my hydrocarbon. 2 of them are left as my hydrogen gas product. Okay. And then the other one here, ethane, is 2 carbons bonding to octane. 1, 2, 3, 4, 5, 6, 7, 8. If you're going to draw them, this would be C2H6 reacting with C8H18. And then my product, again, hydrogen gas plus, this would make C10H22. So that would be decane. And if I draw that, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Line diagrams sometimes are the easiest way to draw just your alkane hydrocarbons. Okay? And that's it. That is reforming, the opposite of cracking. I believe that is the final, just a quick review here of all of our reaction types. Okay, cracking and reforming down here. The polymerizations that we looked at, addition and the 2 condensation. And then the other videos went over those other reactions. So that is it for organic reactions and the end of the organic chemistry unit. Thank you very much for watching.